Hello and good morning everyone. Today I, Shresha, a third year undergraduate student at IIT Madras, am going to be sharing a course summary of the course Photonics, which is EP3200. So let's dive straight into it. So, what is photonics? Photonics is essentially a branch of optics wherein you are studying more about the application of all phenomena such as detection, generation, and manipulation of light in the form of photons through phenomenon like emission, transmission, modulation, amplification. Basically, photonics is a basket which covers everything which involves a manipulation of light in some form to the other and using that light's energy for other purposes. So, understanding why photonics is needed. So, there are wide applications of photonics ranging from solar panels to generate energy to interferometers to photography and image processing. Moving on. We also have applications such as fiber optics, which is now being used in the most upcoming technologies such as 5G data and stuff like that. Along with that, it is used in lighting and decorations as well as medical analysis and diagnosis. So many treatments which are done in today's time are helped and assisted through photonics, along with the screening of the bodies, be it any sort of body scans. It is all facilitated through technologies related to photonics. So coming to the definition of how this has evolved as a field. So initially, the things were treated as rays, like the light was treated as ray. Followed by that, we came up with the wave optics, which was then encircled by the electromagnetic optics, which treats wave optics as a subset of itself. And then we came up with quantum optics in the 20th century, wherein we got to have a much better understanding of how optics and photonics works. Right. So starting off with the most basic level, which is ray optics. So ray optics or geometric optics is the model of optics that describes light propagation in terms of rays, wherein ray is essentially a line which is has a direction and has a defined starting point. So the common phenomenon included in ray optics is reflection and refraction, both of which we'll be studying very soon. So coming to the laws of reflection. So there are two laws of reflections. One is that according to the law of reflection, the angle of incidence is equal to the angle of reflection. So when a light is incident on a reflecting surface, the angle at which it is incident with respect to the normal is same as the angle to which it gets reflected with respect to the normal. Secondly, the incident ray normal to the surface at the point of incidence and the reflected ray all lie in the same plane. So when there's a light falling on a reflecting surface, the ray coming in, the ray getting reflected out, as well as the plane of incidence which is normal to the point of incidence, they all lie in the same plane. So these are essentially the two laws of reflection. We'll see a demonstration for the same very soon.
Let us learn about laws of reflection.
So as we can see here, here we're going to see a demo of how the light gets reflected from a reflecting surface. And as the definition is shown on the screen, yeah. So here as we can see that the light after hitting the surface, it is making an equal angle with respect to the normal. And yeah, the line which is hitting the incident surface is called the incident ray. And the one going back is a reflected ray. Coming to the second law. So here as you can see, the normal to the plane of incidence as well as the inflected and incident and reflected ray all lie on the same plane while maintaining the law that the angle of incidence is equal to the angle of reflection. Moving on. Right. So that was more about the laws of reflection. Moving to the refraction part. So in refraction, the main law which is followed essentially is the Snell's law. The Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. So here what we see is when a light travels from a lighter to rarer or a rarer to denser medium, we see that the light tends to bend towards the normal, while the other way around we have the opposite. So what this basically means is like the direction in which you're traveling, like the perpendicular direction, the velocity is maintained. So accordingly, the light adjusts its angle in order to make sure that that law is being satisfied. So here, as we can see in the case of refraction, as shown in the image, the light bends towards the normal. So that is what the Snell's law basically states. So coming to the phenomenon related to refraction, first comes is the total internal reflection. So TIR, which is a total internal reflection, is the complete reflection of a ray of light within a medium such as water or glass from the surrounding surfaces back into the medium. So what happens here is beyond a certain angle, when you try to have a refraction, the sine law cannot be followed. The reason is because sine theta takes values between 0 to 1, and in cases wherein the n1 by n2 ratio makes situations wherein the sine theta value has to be greater than 0, greater than 1, in those cases what happens is you tend to have an internal reflection. So the light bounces the surface, and instead of getting refracted, it will come back to the same medium, and this is what essentially total internal reflection is about. So it has a lot of applications including fiber optics, which we'll study very soon. So just to show you an example, right? So in this example, we'll be learning about how this works. Yeah. So here is a glass medium, and we'll be showing light. So here, when the angle of incidence is about along the line of normal, we see there's very little deviation. Now, as we move the angle, we can see the angle with respect to normal, the deviation which is coming is increasing gradually, which we'll see will be maximum at the critical angle, which is after which we start seeing some sort of internal reflection. The deviation tends to be maximum here, and now as you can see there's a reflection of light. So at this point we see that there is no light being refracted out, but it's all being reflected through this. And as we keep increasing the angle beyond the critical angle, there will be no change, as it will all get reflected back into the same medium. So coming to the applications of total internal reflections. Fiber optics is one of the most trending and the most happening topics right now, wherein there have been numerous applications, be it for transmission of high speed data to even setting up networks such as 5G, which is being laid underground right now. So, fiber optics is essentially the science of transmitting data, voice, and images by the passage of light through thin transparent fibers. And optical fibers are usually made by silica based glass or plastic that are insulators and therefore have no currents flowing in them. So essentially what happens is you have two layers. One is the core, other is the cladding. And you keep very similar refractive index such that most of the light travels in this direction. So not much of a gradient is needed. So for example, the typical values of silica based in what do you call refractive indexes are about 1.44 and 1.47 to ensure there is total internal reflections for all lights coming at very high angles with respect to the normal. So that is the main principle behind fiber optics. So fiber optics is one of the cases, but now there are multiple waveguides through which you want your energy of light to pass through. So examples of the same is a branching waveguide, wherein you have a light passing and after that there's a split. So you split the incoming light into two branches. After that, there is a crossing waveguide wherein you will want the energy of two to be combining at one point and diverging back again from that intersection point. Then directional coupler are when two lines tend to come close, wherein they don't exactly meet, but there is some sort of energy exchange through the what do you call wave optic scenarios. So that is about that. Then multimode interference coupler is something we study at a later point, wherein we'll have a better knowledge and understanding of what a multimode means as well as how interference works. Max interferometer is something also we'll study at a later stage. And coming to the other part, so polarization filters is something wherein you would want to add a phase or some sort of angle when you're making it pass ahead. So the same will be studied in further detail when you would want to change the Jones matrix, which we call it. So you use a Jones matrix to alter the conditions to make your light come out in a phase which is required and needed in the further stages. So that was it about ray optics. So let's come to the parent of ray optics, which is wave optics. So wave optics is essentially the branch of optics that studies interference, diffraction, polarization, and other phenomena which approximation of geometric optics is not valid at. So in certain cases, like there are certain phenomena which cannot be explained by a light going as a ray. So that is wherein wave optics steps in. So as you can see here, uh, the light is treated as waves of different varying wavelengths. So as we see for the Vibgyor range, there are wavelengths going from 400 nanometer to about 700 nanometers. So what this essentially means and how this works, let's study that further. Yeah. So in wave optics, here like there are multiple types of wave fronts. So as I said, these are the light from a given source is going to travel as waves. So the wave can be in multiple forms. One can be a spherical wavefront wherein there is a point source from where the light is going to travel in all directions equally. So that is when we have some sort of a what do you call spherical wavefront. Coming to cylindrical wavefront, so if we have a line which is emitting light in all directions, so with respect to the line, in all directions radially, the amount of energy being radiated is going to be same. So wavefront essentially means a locus of points wherein the energy is same. So similarly, in this case, if it's a line, assume it to be infinite line, and obviously we'll have on all radial points the amount of energy to be the same. So that is where we get a cylindrical wavefront. Coming to a plane wavefront, when our source of light is somewhat of a plane itself, the light will travel in front of it in a what do you call same sort of phase. So that is when we have a plane wavefront being generated. Right. So few of the phenomenon which only wave optics can be explained is diffraction. So what diffraction essentially means is diffraction is some sort of bending of waves around the corners of an obstacle. That is, in these cases, the obstacle size is very much comparable to the wavelength of the light. And in these cases, we can see that a bending of a light wave is something which cannot be explained by ray optics, as ray optics assumes that light always travels along a straight line. And if that was true, a light cannot bend around an object. But this is something which can only be explained by wave optics, wherein you can see that as in the shown in the diagram above, that there is some sort of bending of light around smaller obstacles, due to which we can see a diffraction pattern at the end. Also, diffraction grating is something which is a very good application of diffraction, wherein it is an optical component that serves to periodically modulate the phase or amplitude of an incident wave. So using this we can get the desired diffraction patterns which we need, which it has a lot of application on a later stage to study the intrinsic properties of light. And also, a diffraction grating is constructed using a transparent plate with periodically varying thickness of different refractive index. So what essentially happens is you're inducing some sort of a optical path at the end of it, causing the diffraction to show its properties. Right. So coming to another very common what do you call phenomenon which can only be explained by wave optics, unlike that of ray optics, is interference. So as we all know, be it the case of electric waves, electromagnetic waves. So interference is a phenomenon wherein there is some sort of superposition of waves. So diffraction and interference are the two phenomena which could be very prominently seen in the double slit experiment, Young's double slit experiment, and wherein we see that initially the wavefront is diffracted as it passes through each of the slits, and this causes the wavefront to spread. So as you can see, S1 and S2 will act as some sort of a point source from where somewhat spherical wavefronts are coming out from those 2 points, but only in one direction. So it's more like a conical, like a conical part of a sphere. And the interference pattern of this is seen on a screen far apart, wherein you will see alternating minima and maxima, which are caused due to the path difference induced. So based on the path difference and the formula, you can see a path difference induces a phase difference, which will obviously depend on the lambda, and this will cause interference patterns ranging from minimas to maxima. The minima being if the two light sources are same, the minima will have no intensity, which means a lack of light, whereas a maxima would contain 4 times the intensity of light because the amplitude is going to be doubled. So that is more about how interference work using the Young's double slit experiment. To get a better idea of this, let's see a demonstration for the same. So here, this is a source which is creating light, and through diffraction, we'll see the two slits which are there here. They're going to be become point source, which is S1 and S2. Now, S1 and S2 have been made the point sources. Now, at alternating minimas and maximas, you'll get constructive interference based on the phase difference as mentioned earlier. The phase difference is calculated by calculating the path difference and accordingly adjusting it with the lambda which we have for the light. Central maxima lies at the midpoint of these 2 points, wherein it is confirmed that the optical path is going to be same for both the points, and thus there will be a phase difference of zero. Destructive interference takes place at the points where there's going to be a zero phase. Sorry, zero magnitude of light, because the phase is a multiple of pi, which means they are both out of phase. Moving on. So based on interference, we have a very good application of interferometers. So what interferometer essentially means is it is an optical instrument that splits waves into like a splits a wave into two using a beam splitter. So beam splitter will be used to split an incoming wave into two directions, and then once it has been split, the two waves coming out will be traveling unequal distances or unequal optical paths more importantly, and then they will be redirected to come to the same point. After coming to this point, what we see is a interference pattern of these two. So this has a lot of application, getting the desired intensity as well as waveform you want through a given beam of light just by adjusting the position of the mirror or changing the optical path that the two splitted waves are going to travel. So as you can see here, the same formula which is used for interference is used here. The only difference is here only one source of light is needed, which is being split through a beam splitter, and then we are seeing the interference pattern of the same. So the most common interferometer which is studied recently is microsync interferometer. So as you can see in the structure, what we have is a beam splitter at the starting of the what do you call source. When the laser enters it, it is split in two directions. One is upwards, other is towards the same direction. And now what happens is through M and M, which are the two mirrors, it will go and travel the distance and come back. So depending on the distance which is being traveled, we will have a optical path which is induced, giving it a phase difference. Now, if the phase difference is such that it's a multiple of 2 pi, you'll have a maximum, which is a maximum at the photo detector end. Whereas if it's a multiple of pi, you'll have a minimum which is almost zero intensity. So based on the optical path and the thus induced phase which is coming up, we will have a pattern of interference based on the distance which is being traveled. So as it is rightly mentioned here, the process which is involved is optical instrument that splits a wave into two ways using a beam splitter, delays them by unequal distances or unequal optical paths, and then redirects them using mirrors. Recombines them using the same beam splitter, and then it detects the intensity of the superposition. As you can see at the bottom, there is a photodetector which will be seeing the intensity pattern and how the interference is taking place. So let's see a demonstration for the same. Yeah. So here is the laser light going in. These are the two mirrors at the two ends, and by changing the distance of the mirrors, we can see how there is a changing intensity which is coming to the photodetector. These are the two lights being split in two directions. Reflection through the mirror, meeting back at the beam set and combining as one wave, and showing varying intensity as per the optical path induced. As you can see by changing the optical path, how the intensity is changing. Right. So moving on to the next type of interferometer, which you know what, which is the Mach Zehnder interferometer. So this works on a principle of adding, as I mentioned, the main variable here is the optical path more than distance. So here what we do is we induce a difference in optical path by adding a certain medium wherein the which is different to the normal medium. So as you can see in the definition, a phase difference of delta phi is being produced in the sensing arm by changing the effective refractive index through a certain part of it and thus getting a different optical path travel. And here, as you can see the diagram at the bottom, like by having a different optical path, we are getting a phase difference of delta phi, which will then be used for the interference pattern, as we know the cos phi formula. And accordingly, we'll get to see different interference patterns based on how much the delta phi is being induced. So as you can see in the diagram at the top, we have a line being splitter, beam splitter, and after that there are two mirrors, one which will reach it directly to the other beam splitter where the light gets combined, while the other is going to have some sort of a difference in optical path by traveling through a medium wherein the refractive medium or the speed of light is not going to be exactly the same, due to which some sort of optical path is induced and we can see a interference pattern on the screen based on the difference that we're getting. So showing a demo for the same. So by using a compensator which we saw in the previous diagram, by changing the amount of field we have, since light is treated as a wave here, so we'll have some sort of disruption in the amount of path being traveled because of changing the refractive index by just inducing some sort of an electric field. Based on the value of the field which you're creating, we'll have different sort of refractive index changes by which you can change the delta phi according to the value we need. The more the field effect, the more it will be slower because obviously the maximum speed is in vacuum with no other fields. The moment you start changing parameters, that is when the light keeps on getting slower and slower. So while these changes are insignificant, when scaled over larger values and since the wavelength is so small, the phase which is induced through even small changes has become significant. This causes a phase change between the incident like light coming from the top layer and from the bottom layer. So as we can change the field, we can see the intensity at the output being changed significantly. Here it is shown as out of phase. Now as you can get back to the normal value, we're getting a maximum of the intensity. Yeah. So the next type of interferometer we have is the Sagnac interferometer, which works on the principle of the Sagnac effect. So what Sagnac effect basically means is that when you rotate a light in a certain direction and run in two different directions, so the paths travel optically will get added even though by an insignificant amount, but when the medium is rotating, what happens is the amount of path you have to travel is a bit greater for the light, even though it's insignificant with respect to the speed of light. But taking into account that the wavelength of light is of the magnitude of 10 to the power minus 9 meters, we can see that this is something which is still very significant compared to the normal scenarios. So this can also induce some sort of a phase difference, which is significant when scaled up at a larger speed. So Sagnac interferometer is an optical instrument that splits a wave into two using a beam splitter like all the other interferometers. And after that, it delays them by unequal distances, not by making them travel different paths, but rather by rotating the medium which we have, by inducing us extra rotationary path. So what is happening here is one light which is traveling in the same direction as the motion will have a different path to be traveled at the time of meeting compared to one which is traveling the opposite direction. However insignificant that change is, the point to be noted is the wavelength is very small. Thus, even a small difference in paths will lead to a significant phase difference. Right. So that is where we conclude our wave optics discussions and move on to the even more complex topics, which is the electromagnetic optics. So there were again many more. For example, as we saw in the Max and interferometer as well, we could see that due to electric field, there's some sort of variation in the medium. So we'll try to understand such phenomenon and many other things in a much more detailed way through electromagnetic optics. So what electromagnetic optics states is a light is um, nothing but an electromagnetic wave, which is comprised of electric field as well as a magnetic field, which are perpendicular to each other and which are also mutually perpendicular to the direction of propagation. So the direction of propagation can be found by taking the cross product of the electric field and the magnetic field, and the equation of an EM wave is as follows. So here E and B are the values of the electric and magnetic field, and this is the general wave equation for any parameter. So here the variables we have for the two electric and magnetic fields are E and B. So as you can see, 1 upon C naught square, where C naught is the speed of light into what do you call this equation. We can see that this is something which is satisfied at all points of the wave. And also, when it comes to electromagnetic optics, the most important things to take into account are the Maxwell's equation. The four Maxwell equations which are shown here. So one is two of them are related to the flux of electric and magnetic field, while the others are regarding the amount of curl we are having, and as well as the effect of generating electric field through a magnetic field and vice versa. So as we see at the bottom, like there are different ranges of frequency as well as wavelength, which would give us different types of light with different types of application and strength. Right. So coming through certain phenomena which is related to this, so polarization. So as we know that light has two directions, right? So electric field and magnetic field. So we try to polarize the field along only one direction, which is let's say a given direction of electric field is what we need, or a given direction of magnetic field is the only type of light we want to accept. So what we do is polarization is essentially a property applying to transverse waves, for example, electric and magnetic waves, wherein you would want to get a particular geometric orientation of the ray which is being sent through, and what do you call? You want the vibration of light, which is the oscillation of light, to be in a particular wave only, only in a single plane. So, for example, when you have a linear polarization, if you send a light through a torch which has light going in all directions, you would get a output which you can see in the first photo in a only linear phase. So, only one particular direction of light, that is electric field in only one direction, and corresponding magnetic field in only one direction will be available at the other end. Similarly, if you want a circular polarization, we have circular polarizers wherein only two directions are allowed, and that too which are perpendicular to each other and have the same amplitude, because thus giving out a circular output. And elliptical is all the cases other than this. So let's study this in further detail. So this is a light source which will be emitting the light, which will then be polarized by a polarizer. A polarizer is also known as a polarizing filter. As we can see, there were multiple directions when the light was coming in. But after passing the polarizing filter, only one direction of light has been able to pass through, and as you can see at the filter as well, only one direction would have been allowed. And that can be chosen according to your will, and different geometrics, be it circular, linear, or elliptical, can be achieved through using different PNCs of polarizers using the logic of polarization, that is only letting through one direction of wave. Moving on. So yeah, discussing the three types of polarization we know till now in further detail. So linear polarization occurs when the what do you call phase difference between perpendicular polarization is a multiple of pi. So for example, if there are two lights which are either anti-parallel or parallel, the magnitudes will get added up or subtracted while there being no direction, no component in a perpendicular direction to it. So all the energy is going to be along the same straight line, be it in a destructive way or a constructive way. So that is the case of linear polarization. Coming to circular polarization, as we know in a circle, we can define it by what do you call a sum of sine and cos. So what we basically need is two ways of the same amplitude, which is the same energy, which are separated by phase distance of phi. So that is how we define our normal circular equations, which is cos omega t and sin omega t terms for the x and y respectively. So we will be having a changing x and y values according to a sinusoid, or basically any polarization wherein there's a pi by 2 phase difference and necessarily the same magnitude. And all the cases other than these two very specific special cases is covered in an elliptical polarization. As you can see that even in the second case wherein the phase is not pi by 2 but the magnitudes are equal, there will be some sort of increase and decrease of the distance from the what do you call center line, as well as if the phase is even pi by even if the phases change, there will be a variation in the amount of distance being traveled. So again, all cases other than these two special cases can be generalized to elliptical polarization. Right. So how to treat and manipulate these waves which we're getting? So the best way to do it is matrix representation. So we can show these filters as a matrix. So what this essentially means, when you have an incoming wave of, let's say, amplitudes in x and y direction are known, you would multiply this with the Jones matrix, which is the T matrix here, to get the desired output. So, example, if you want a linearly polarized light, so what you'll do is you'll only pass through one direction and make all the three others zero. So all components along the direction in between as well as the perpendicular direction is made zero, as you can see here. Similarly, if you want to use a wave retarder to add some sort, make one signal pass as it is, while the perpendicular direction should be phase changed. So what happens in the second case of wave retarder is one light direction will go normally, while the other will have a phase difference of t or tau, which is here, as you can see in the Jones matrix here. And polarization rotators are something which are used to change the direction in which the light is rotating by a certain angle, which is theta here. So this is something which can be generalized to all possible values of theta, and these three, along with many others, can be used to just create a Jones matrix to give the desired output based on the input you're getting. Right. So here, as you can see, there are multiple vertical phenomenon which can now be defined in terms of TE and TM. So in the Jones matrix itself, we know there's some sort of reflection as well as transmission. So the exact values of this using the laws of reflection and refraction can be derived to this, wherein Tx, Ty, and Rx, Ry are the Jones matrix parameters, and these values are determined completely on the basis of the angle of incidences as well as the refractive indexes which are used for the two mediums. So as you can see here, N1 and N2 are the two mediums being used, and the light is being incident from the N1 medium to the N2 medium. So whatever phenomenon happens beyond this in terms of transmission and reflection can be easily determined by these formulas to get the reflection and transmission Jones matrix. Right. So coming to few of the most important applications of these refraction and these transmission, what do you call modes? So the Brewster's angle. So as we know, whenever light is incident in a medium, some sort of light is refracted, some is reflected, and most of it is transmitted, as we know. But to come through a situation wherein what we want to achieve here is through booster angle, we want an angle of incidence at which light of a particular polarization is perfectly transmitted through. Like there's no sort of lights coming out in the different directions through a transmit directed surface. So in this case, as you can see, when the light goes through, there is nothing. There's just one source of one direction of light coming through, with no other sort of transmission in other directions. So that is what we call a perfectly transmitted light through a transparent dielectric surface. And this angle is achieved as the tan inverse of the ratio of the two mediums. So the medium it is going to divided by the medium it is coming from, the tan inverse is what is the Brewster's angle for any general scenario. So this is to get a perfectly polarized light. So we'll see an example for the same. So here this is the reflected component of light. Well, there is some sort of transmission as well. But when this light is getting transmitted, there is some sort of components along the other direction as well. So this light is called a partially polarized light, wherein not all energy comes along the same direction. But when we change this in a way so that we get the Brewster's angle, which is tan inverse N2 by N1, we find that the light is completely polarized because there is no particular component to it. Right. So coming to the parameters and the values which we care about while we are studying these parameters. So one thing which is comes on the top is the fiber V parameter. So what this essentially gives an idea about is the number of modes of fiber and the propagation constant. So V, as you can see, the formula is defined as 2 pi A upon lambda naught into Na. So what is Na? Na is a numerical aperture which is root of the refractive index of the bigger medium, like the greater medium, minus the square of the smaller medium, and the number of modes of which you're getting is essentially defined by m is equal to 4v square by pi square plus 2. So here v is the fiber v parameter, and as you can see from the formula, so unless v is greater than 2.405, which is making it greater than 4 by pi square, we will have a single mode transmission of light. So in case we want a multi-mode transmission, we need to have v greater than 2.405 as a condition. And as you can see some sort of a ceiling function here just being made of the number of modes. Right. So that was more about how wave optics and its phenomena and defined. But when we came into the 20th century, there were many like hypotheses which were coming through. For example, photoelectric effect, which could not be defined by wave optics or ray optics. So that is when quantum optics came up as a topic, wherein quantum optics is basically a branch of atomic, molecular, and optical physics dealing with how quanta of light, known as photons. So, was a term which was tossed to represent a packet of energy, a light packet of energy, which travels when we talking about light coming through. It is basically photons traveling and hitting us. So these photons, we will study how these photons are going to interact with atoms and molecules and the effect it has. So an energy of an photon is defined in terms of packets of energy, and that packet of energy is defined as h nu, wherein h is the Planck's constant, which is about 6.6 10 to the power minus 34, and nu, which is the frequency of light. So this is the energy of a single photon of a given frequency nu. And knowing that the fact that the average what do you call visible light has the valence of about 400 nanometer to 750 nanometer, most of the average like energy of an visible light is of the range of 10 to the power minus 19 joules. Right. So the important phenomena which was observed in quantum optics are the three of these. So absorption of light. So earlier when we saw light as a ray or just a wave without energy, many things such as photoelectric could not be explained obviously. So what we see is absorption. So if the electron in an atom is initially in a lower stage and we see that a photon comes and hits it, many times it happens that the electron will be absorbed, like electron will absorb the energy and go to a higher energy level. So what is essentially happening here is photon is giving all its energy to an electron to cross a certain energy barrier and go to a more excited state. So that is about absorption. Now coming to spontaneous emission. Spontaneous emission is when an electron is in higher state. So it is not in its down state, it is in an excited state. And it spontaneously, just to release energy and just to become more stable, it will come back to its lower state. And what happens meanwhile is the energy is not released in the form of heat as you would normally expect, but rather in the form of a photon coming out of an energy which is equal to the difference between the two energy state levels. So as you can see in the definition here, electron atom in a higher energy level will decay spontaneously to the lower level because it is more stable. So it's a spontaneous process and it will release energy in the form of photon. So this has applications in many cases such as for example semiconductor optics. So wherein by releasing energy of certain and coming to a more stable state, you are releasing energy in the form of photons. The energy is coming out in the form of photons which can be used as light for different purposes. And then comes stimulated emission, which is one of the more interesting phenomena wherein a light of a certain frequency is thrown at what do you call a electron in an excited state. But now what happens is when this absorbs it, it will release two photons. So, unlike the spontaneous emission case, this is more of an induced emission wherein you're forcing it to happen. So, when a light is hitting an excited electron, instead of passing just one, it will pass two, which will also include the energy which is coming from the photon. So, the two energies is coming out is one is that of the excited electron as well as that which was incident. So, by absorbing it for a very small fraction of a second, you're being able to basically replicate the same thing over a like larger magnitude, which is twice the magnitude. So as you can see in the definition, when an electron in an atom is an upper energy level and radiation is done is comes across radiation. So whatever the energy difference is, when it gets hit by the same amount of energy, it's going to release two photons of the same energy. So this process is like more like the stimulated emission because it is something which you are inducing. You're getting this induced to have two photons come out, and this can, in some sort of sense, be defined as the inverse of absorption because in absorption, what happens is one light is hitting, but here, while it is hitting, it is releasing two of the same value. So the net is outflux of two and influx of one. Right. So coming to fluorescence. So fluorescence is one of the phenomena which is again only defined through quantum optics. So fluorescence is the phenomenon wherein a material emits light at one wavelength while you illuminate at another. So what happens essentially is when you hit a particular material or the photon of that material with a high energy light, it will slowly settle down to a lower state, and then finally, what happens is it will, if it absorbs energy at a lower wavelength x, it will release energy at a larger wavelength y, which is at a wavelength wherein less energy is being coming out, while some amount of energy is absorbed by that by some sort of transition of states, and then it will release out a lower energy state and give us out light. So, for example, in this case, like the materials that show these properties are called fluorophores or even a fluorescent material, which has two basic properties. Absorb light at a lower wavelength, which is excitation, meaning lower wavelength here essentially means at a higher energy, and then it will emit light at longer wavelengths, which is at lower energies, and this is called emission. So time taken for fluorescence on an average is about 10 to the power minus 9 to 10 to the power minus 6 seconds, which is almost instantaneous to some extent. Right. So working of fluorescence. So as I mentioned earlier, so when light of a greater energy, so as you can see in the green wave is of a greater energy. It will have some sort of relaxation. There will be some sort of state change to measures back to its initial like a lower energy level, and after that there will be fluorescence. So the red light has lesser energy, greater wavelength, but this leads to some sort of visible light which is coming in the range of 10 to the power minus 10 to 10 to the power minus 6 seconds right after the hitting of light, and we can see some sort of fluorescence. The timing, as you can see here, there are multiple phenomena which happens when a light is incident and light is coming out. So phosphorescence is something which takes of the order of about milliseconds to kiloseconds, whereas fluorescence is of the order of nanoseconds to microseconds, and many other things such as the vibrational settling and other things are something which takes it much faster, because after multiple rounds of vibrational settling is when we come across phosphorescence. So this is more about the timing diagram of how these phenomena are occurring at fluorescence. Right. So coming to laser. So laser is something which employs the principle of stimulated emission. So the full form of laser is light amplification by stimulated emission of radiation. So a laser is basically a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. So let me break this down to you. So as you can see in this uh, diagram, when we are incident with only one light, through continuous stimulated emission, we are increasing the number of photons while having the same energy input. So the thing which are required here are two. One is excited electrons in the top state, as well as a very small amount of photon, because most of the energy is going to be just passed on forward, and the energy is going to be coming out of settling of electrons, and at the same time of one initial energy which has stimulated all these emissions. So few of the common elements used for this is the Cr3 plus ion, because that tends to give the one of the best properties, and it has a wavelength of about 694.3 nanometers, which is again in the visible range. Right. So there are two types of elements we will be using in such cases. One with the direct band gap, other with the indirect band gap. So what this essentially means is, so uh, direct band gap is a case wherein the minimum difference point. So the point where the difference is minimum, which is the band gap, is achieved such that the two corresponding particles have the same momentum or the same wave number, which is k. Whereas the indirect band gap case is where the momentum is different. So it is much more convenient to carry in the case of direct band gap. For example, the case of GAS, which is gallium arsenide, compared to the indirect band gap of the cases such as silicon. So for laser applications and simulated emission, the ideal thing to use is ones with direct band gap. So as I mentioned earlier, the two energy sources are the pumping, which is moving of electrons from a like more stable state to a higher state, which does allow more stimulated emission in a like more of a chain reaction manner. So that along with light is what creates a laser. So how is this pumping of electron achieved from the ground state to the excited state? So here is where the optical pumping comes into place. So pumping is basically augmenting this signal through some sort of energy, be it gas discharge or even an electron beam or an ion beam, or chemically as well through some sort of flame or something. We can get the electron to a higher state, which can then be used for stimulated emission one after the other. So that is what like pumping of electrons is about, which will then be used for the laser stimulated emission. Right. So coming to the gain. So as we know, the amount of light which is traveling at every successive stage is increasing. Why? Because of the release of energy of electrons from a higher to lower state, and accordingly more stimulated emission taking place as we go forward. So gain is similarly defined as the amount of change in the intensity of photons going ahead with respect to change in the width of it, which it is traveling. So in this case, like a lot of laser amplifier pumpings, such as a flashlight or something, is used to get into the higher state, followed by which you can get even greater gains. So more the amount of pumping and the more amount of stimulated emission we are having, the greater is the gain which we're going to achieve through this. Yeah. So there are two types of pumping which take place mainly. One is the four-level pumping and three-level pumping. So based on the as we know about the rate determining step in chemical reactions, similar is the case here. So based on the what do you call energy transition which takes a maximum time, we can accordingly place our electrons at those levels where we know this will stay here for a longer time, and we can accordingly whenever we pass the light, it gives us a bandwidth in which we can pass the light and still get the stimulated emissions results. So there are two types of pumping. One is four level pumping, wherein there are two short lived levels along with a ground state and one long lived level. And there's a three level pumping, wherein there are only three stages. One is a short lived level, long lived level, and the ground state. So based on the material which are having the type of needs we have, and as well as the bandwidth you can give, like in this period of duration, you can come and hit the surface to get the stimulated emission going. We can accordingly design different types of pumping and get the desired values needed. Right. So statistical properties of light. So the light which is coming out of a bulb, as you can see, which is hitting my face, that has a lot of properties, but which are not exactly the best properties. So for example, a bulb will release light in all directions. So that is not directive. Like it is not traveling in one line. It's going to be in all directions. So it is not directive in nature. Secondly, monochromaticity. So unless it is a very like professionally made light bulb, you will have like most of the things, for example, white or all the other colors are made by some sort of combination of different wavelengths. So more often than not, it is not monochromatic in nature because due to some level of reflection from different surfaces, light coming here, you can see even my face is not monochromatic in nature. Reason because there is reflection, all other components wherein causing the light to be of different wavelengths, like net wavelength as well as different intensities, causing the light not to be of the same color. And thirdly, coherence. So coherence basically means that the light has a constant phase and a similar wavelength. So that is also something which is noted because as we know, different lights coming with different frequency are because there are different refractive indexes in the same place due to hot and colder air. So there is no sort of coherence of light as well as the phase difference are varying. There are different frequencies. So coherence of light through normal sources is also not found. But when it comes to laser, all three criteria are met simultaneously, as you can see here. Directivity, as we know, when you're moving forward, there is the simulated emission happening in the same direction, causing the light to only travel in the same one particular direction. Thus, it is completely directive in nature. Secondly, monochromaticity. So, since it is the same material releasing these photons, so in the previous case we saw CR3 plus ions. So it can only release one particular wavelength of light, unlike the normal light, which is 694 nanometers approximately. So it has to be monochromatic because it's a laser which is coming out from the same source. Also, it is coherent because, as I mentioned earlier, it is the same wavelength which is coming out from the CRC plus ions. Thus, it is coherent in nature as well, and it runs parallel to each other because it's more directive as well. So that is the properties of lasers compared to a normal light, which can be used for more professional applications and more precise calculations of certain things. Because here you can get the exact parameters in the exact direction you want. Right. So coming to the semiconductor side of photonics. So as we know, we saw the application of how getting photons through electrons with some sort of energy release is ideal in most of the photonics application. So here is where enters PN junction and other semiconductor applications. So what a PN junction essentially is the juncture of a P and N type semiconductor, wherein P type is a semiconductor which has more holes than electrons and N type is more electrons than holes. So when these two combine, there is a depletion layer in the middle wherein there is a diffusion. So to balance this mismatch that we have, the electrons move towards the P side and the holes move to the N side due to some diffusion effects, and this creates a potential gradient. So as you can see in the definition here, it acts as a diode and can also serve in electronics as a rectifier and a voltage regulator. And this has applications in many cases such as LEDs, so light emitting diodes, and solar cells and photonics. So, as I mentioned, for a PN junction has a P-type and N-type semiconductors. and p type has abundance of holes, whereas the n types has a abundance of electrons. And now we'll study how these properties can be used to further improve our study of photonics and generation of light. Right, light emitting diodes. So as you can see in the photo here, light emitting diode is a forward biased PN junction which is fabricated from a direct bandgap semiconductor material that emits light by electroluminescence. So as you can see in the diagram below, there is a cathode and an anode. There's a bond wire. There's a epoxy covered lens and a ready chip. So when it is forward bias, what forward bias means is there is a positive side connected to the p side and negative to the n side. So in this case, the potential barrier gets reduced and the electrons and hole are tending to combine even more at the depletion layer, which is the layer between the p and n junction. And because of this combination, light is going to be emitted because there is a release of energy. When p and these what you call carriers are combining, there is a release of energy, and this is seen in the form of light, photons, which is light particles energy. So this, just to prove how this works, we have a photodetector to measure the amount of optical energy which is coming out. So photodetector is basically a device that measures the photon flux or the optical power by converting the energy of the absorbed photons into a measurable form. So through photoelectric effects and other phenomena, we know that we can convert optical energy to electronic energy. And electronic energy has multiple sophisticated ways to measure it. For example, beta ammeter, voltmeter, we can get the amount of, we can quantify the amount of energy is coming in an optical format and accordingly do calculation based on the same. So in this case, by absorption of photons, electrons are released to higher energy states, and these carriers move to produce a current which is then measured through a current indicator, and there is a voltage source also attached to measure this measure the same. So what is a photodiode? So based on the PN junction definition which I've shared and how photoelectric effect works, this is the inverse of photoelectric effect. So wherein photoelectric effect we had like some sort of application of photoelectric effect itself, but in a more sophisticated way. So here what we're doing is we are having incident photons, and due to this we are having energy being bombarded. So what is happening here is a photodiode is a light sensitive semiconductor diode. It produces current when it absorbs photons. So it's photoelectric effect essentially, but to induce electricity. So the passive photodiode allows light to reach a sensitive part of it. So for example, the repletion layer when most of the potential difference is formed, and then this energy will be used to create some sort of potential difference and make the electrons flow throughout the circuit. So photodiode is a PN junction whose reverse current increases when it absorbs photon. And although PN and PIN generation diodes are generally used, like they do not exhibit any sort of gain. So that is a very important property of photodiodes, which we'll see in the later points. So this is a demonstration of photodiodes, how it will induce electricity just by having photons incident on it. This is an application of photoelectric effect in some sense, which we'll see in this video. So when light is incident, we see some sort of electrons moving out in the circuit. This photon will lead to excitation and additional energy, causing creation of holes in electrons. The holes remain stationary while the electrons start flowing in the circuit. And this causes the flow of current, leading to voltage difference and thus some sort of an electric power being generated. So coming to avalanche photodiodes. So as is on the case of laser, how electric stimulated emission can lead to much greater values compared to the initial input, just if we have some sort of electronic pumping being done. Avalanche photodiode works on a very similar principle, wherein we have a cascade of what do you call? We're cascading the effect of a single photon, and by just adding weak light, we have a set of much stronger, electron being flowed by just exciting it to a higher stage and leading of one electron to multiple more electrons as it moves forward through the gain. So this is what an avalanche photodiode does. So unlike the normal photodiode, this has some sort of gain being exhibited because there is stimulated emission principles being applied here. And this device is configured as a strongly reverse bias photodiode because in a region where the junction electric field is large. Here, the charge carriers can therefore acquire sufficient energy to excite new carriers by the process of impact ionization. Right. So coming to quantum efficiency. So quantum efficiency is basically the probability that a single photon incident in the device. So especially in the main what do you call junction where most of the most sensitive region is there, you will want to know what is the efficiency like with respect to the amount of photons falling, how many electrons and electron hole pairs are being generated. So that is the quantum efficiency. The ratio of conversion of the number of electron hole pairs being generated is the number of photons. Number of electron hole pair generated can be seen in the form of intensity divided by the electrons, whereas the incident photons can be seen by the power being added divided by the power of individual light, which is h mu. So that is how we measure the quantum efficiency, which is that how much electron hole pairs are being induced with respect to the number of incident photons. Responsivity is another very important thing we take into account because responsivity is something which relates the electric current flowing in the device circuit to the optical power incident in it. So unlike the previous case, this is something which depends on the amount of energy as well as being incident. The previous case, all it depended was the ratio of how much the incident number of photons and the number of hole pairs. So the values of weight and other things were more relevant there. Here, it has some sort of relevance because the amount of energy being transferred is also taken into account. So this is something which is more important when it comes to applications of it, while the previous one was more towards the qualitative analysis that how good is the light being light in generating this electron hole pairs. So yeah, that comes to the end of the presentation. I hope you had an insightful session. And this is Shreesh here, who is EE20B126, a third year undergraduate student in BTech Electrical IIT Madras. If you would have any queries, you can feel free to reach out to me. And I've mentioned my email ID as well. So yeah, it was great having you on board, and hope you had a really insightful and a good learning experience. Thank you.